All right, we're now going to move on to section 5.2. We are going to be dealing with from here on out, from 5.2 through 5.6, with infinite series now. And let's first define what those are. So, basically speaking, what it is I'm going to now take terms and add them up. Whereas before, it was just like the list of them, right? Now I'm going to add them up, and I want to know what happens when I do that, okay? To figure out if it approaches a sum or not, what I'm going to first start with is the series of partial sums. What this is S of k is going to be the sum of the first k terms. So I'm not going to add all of them up, just the first k terms. I'm going to do that for S1 and then S2, then S3, S4, S5, on and on and on and on and on. And I'm going to make a sequence of that, which again is just the list of them. If that converges, then so does my sum here. Okay. So again, I'm going to add up just my first k terms. I'm going to do that for k being a 1, k being 2, k being 3, 4, 5, 6, and then see what's happening there, okay? So let me show you what I mean, okay? Example number 1. For each of the following series, use the sequence of partial sums to determine whether the series converges or diverges. Okay. So I want to know what's happening. This is example 1, part A. This is going to be the sum from n equals 1 to infinity of n over n plus 1. So what's going to be helpful is let's list out what the terms are, okay? So for the sequence n over n plus 1, let's list those out. So plug in a 1, I get 1 over 2, so 1 half. Plug in a 2, I get 2/3. Plug in a 3, you get 3/4. 4 gives me 4/5. 5, 6, 6, 7, on and on and on. So first things first, let's do S1, which is the sum of my first term. Well, that's just my first term, right? My sum of my first term is just my first term. So S1 is 1 half. Easy peasy. S2 is going to be the sum of my first two terms. So my first term is 1 half. My next term is 2/3. So I'm doing 1 half plus 2/3. Common denominator here would be a 6. So I need to times this by 3, times this one by 2. 3 plus 2 is 5, so I get 5/6. S3 would be the sum of my first three terms. So 1 half plus 2/3 plus 3/4. I already know 1 half plus 2/3 is 5/6. And I'm just adding 3/4. Common denominator there would be a 12. I need to times this by 2, which gives me 10. Times this one by 3, which gives me 9. 10 plus 9 is 19 over 12. Then find S4, which is the sum of my first four terms. I know my first three terms add up to 19/12, plus my next term, which is 4/5. Let's see, common denominator there would be 60. So I need to times this one by 5. Oh, geez. 19 times 5 is 95. I need to times this one by 12. 4 times 12 is 48. 95 plus 48 is 143. So 143 over 60. And I can already tell what's happening here. These are just getting larger and larger and larger. It's just going to keep growing and growing and growing, right? This is like 0.5. This is like 0.89 something something. This is over 1. This is over 2, right? So this is divergent. It diverges. Again, because the sequence of partial sums diverges. It just grows and grows and grows. These are just going to grow and grow and grow. That doesn't make sense. Remember to let me know. Example B, we're going to do the same thing. This is the sum from n equals 1 to infinity of negative 1 to the n. So let's list out my terms first. The terms of this sequence. Negative 1 to the first is negative 1. The negative 1 squared is 1. Negative 1 to the third is negative 1. Negative 1 to the fourth is 1. And it will just keep going like that, right? On and on. So S1 is going to be the sum of my first term, which is just negative 1. S2 would be the sum of my first two terms, so negative 1 plus 1, which is 0. S3 is the sum of my first three terms, negative 1 plus 1 minus 1, which is negative 1. S4 is the sum of my first four terms, negative 1 plus 1 minus 1 plus 1 is 0. And you can probably guess here it's just going to switch back and forth, right? Negative 1, 0, negative 1, 0, negative 1, 0, negative 1, 0, on and on and on. So these are not approaching a single thing, right? It's just going to switch off and on. So again, this diverges. Again, because the sequence of partial sums doesn't approach one singular thing. So it's going to diverge. Another example that maybe will make this completely clear. Example C is the sum from n equals 1 to infinity of 1 over n times n plus 1. So let's look at this one. First of all, let's list out my terms. Plug in a 1, that's 1 over 1 times 2. 1 times 2 is 2, so that's 1 half. Plug in a 2, 2 times 3 is 6, so that's 1/6. Plug in a 3, 3 times 4 is 12, so that's 1/12. Plug in a 4, 4 times 5 is 20, so 1 over 20. Plug in a 5, 5 times 6 is 30. Plug in a 6, 6 times 7 is 42. On and on. So first, S1, the sum of my first one term. My first term is 1 half. Easy enough. S2 is the sum of my first two terms. So 1 half plus 1/6. Common denominator there would be a 6. So need to times this by 3. 3 plus 1 is 4. This will be 4/6, which reduces down to 2/3. S3 is the sum of my first three terms. I know my first two terms add up to 2/3, plus my third term, which is 1/12. Common denominator there is 12. I need to times this by 4, which would give me 8. 8 plus 1 is 9. 9/12 reduces down to 3/4. My fourth one is the sum of my first four terms. I know the sum of my first three terms is 3/4. So now add 1 over 20. The common denominator there is 20, so I need to times this by a 5. 5 times 3 is 15, plus 1 is 16 over 20, which reduces down to 4/5. And you can probably see now what the pattern is. 1 half, 2/3, 3/4, 4/5, 5/6, on and on and on. This is approaching 1, right? This is approaching a 1. Therefore, the sum converges to 1. Now, let's talk about what that means, okay? If I kept listing out more and more and more terms, and I added them all up, like 100 of my terms, it's going to be really close to 1. If I tried to add up my first 300 terms, it's going to be even closer to 1. Right? So the sum of all of these terms is approaching 1. Will it ever actually be 1? No, but it is approaching 1. So this sum is equal 1. Once again, if that doesn't make sense, let me know, please. We have this special type of series called the harmonic. What the harmonic one is the sum of 1 over n. So 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth, blah, blah, blah. This is called the harmonic, okay? The cool fact about this is it diverges just very slowly, right? It's going to grow and grow and grow, keep growing, but just really slowly, okay? And this is a helpful fact we are going to use a lot in this class. And so keep that in mind. The sum of 1 over n diverges just very slowly. Another fact, the same algebraic laws that apply to limits also apply to these two. And you'll see what I mean. I'm going to use a few of them as we go on. All right, so example number 2, evaluate each of the following. The sum of 5 over 2 to the n minus 1. Example 2a, the sum from n equals 1 to infinity of 5 over 2 to the n minus 1. So when I say that the laws are the same, what I mean by that, there's a 5 on top that nothing happens to that 5. It's a constant, so I can bring it out front. That's what I mean. It's stuff like that. So now I can just worry about this guy. So let's look at what happens to the sum of 1 over 2 to the power of n minus 1. So let's list those terms out. 1 over 2 to the n minus 1. Plug in a 1 and you get 1 over 2 to the 0, which is 1 over 1, so 1. Plug in a 2, you get 1 over 2 to the first, so 1 half. Plug in a 3, 1 over 2 squared, so 1 fourth. Plug in a 4, 1 over 2 to the third, so 1 eighth. Then I'd get 1 16th, 132, on and on. So my first partial sum is going to be just my first term, which is a 1. My next partial sum is going to be the sum of my first two terms. 1 plus 3 over, I jumped ahead. 1 plus 1 over 2, which is 3 over 2. Then my third term would be the sum of my first 3 terms. My first 2 I know add up to be 3 halves, plus 1 fourth. I would need to make this a 4, so times 2. 3 times 2 is 6. 6 plus 1 is 7, so 7 over 4. Do it again. Sum of my first 4 terms. I know my first 3 terms add up to 7 over 4. My fourth term is 1 over 8. I need to times this by 2. 2 times 7 is 14. 14 plus 1 is 15. Sum of my first 5 terms. I know my first 4 terms add up to 15 eighths. Plus my fifth term, which is 1 over 16. Times 2 gives me 16, which is what I need. 15 times 2 is 30. 30 plus 1 is 31. So if you notice what's happening, the numerator is 1 less than twice my denominator, right? So what this means is this is getting really close to 2. Because again, 2 would be 32 over 16, right? I'm almost there. Same thing up here. 2 would be 16 over 8. I'm really close, right? I'm almost there. I'm getting really close to 2. So this sum is equal to 2 because of that. The partial sums are approaching 2, so the sum is equal to. So this becomes 5 times 2, and 5 times 2 is 10. So the sum of every term, 5 over 2 to the n minus 1, that sum, if I added them all up, would be equal to 10. Does that make sense? Let me know. Example 2b, we're going to do the same thing. The sum n equals 1 to infinity of 3 over n times n plus 1 minus 1/2 to the power of n minus 2. So what I can do is I can break this apart because of the laws I can use, right? So first things first, I have two terms in here, so I can split them up and do two different things. And then I have a constant of a 3 up here, so I can bring it out front. So I can write this as 3 times the sum from n equals 1 to infinity, 1 over n times n plus 1. That's this term. I took care of that one. Then minus, I can do the sum from n equals 1 to infinity, 1/2 to the n minus 2. Now, why is this really nice? This sum right here was the same one I did in example 1c. And we said that was equal to 1. So that's easy. Saved us a little bit of time. If I get one I already know, just use it, right? I already know from example 1c, this is equal to 1, so I can use that fact. Easy enough. So I just really have to worry about this one. So let's list all the terms in 1/2 to the n minus 2. Plug in a 1 first, that's 1/2 to the negative 1, that's 2. Plug in a 2, 1/2 to the 0 is 1. Plug in a 3, 1/2 to the first is 1/2. Plug in a 4, 1/2 squared is 1/4. And then it'd be 1/8, 1/16, 1/32, on and on. So S1 is the sum of my first term, which is 2. S2 is the sum of my first two terms. 2 plus 1 is 3. S3 is the sum of my first three terms. I know my first two terms add up to be 3. Plus 1/2 is 7/2. S4 is the sum of my first four terms. I know my first three terms add up to 7/2. Plus my fourth term, which is 1/4. Times this by 2, which would give us 14. 14 plus 1 is 15. Then go to S5. My first four terms I know add up to 15/4, plus my fifth term, which is 1/8. That would give me 31 over 8, and let's see if I can see what's happening there. Notice I'm getting really close to 4, right? Because 8 times 4 would be 32, and I'm almost there. 4 times 4 is 16. I'm almost there, right? So this is getting really close to 4. So the sum from n equals 1 to infinity of 1/2 to the n minus 2 is 4. So what this means is I can use everything that I know now. So that's going to be 3. Again, from example 1c, I know this sum is 1. Minus, and we just got this sum, was 4. 3 times 1 is 3. 3 minus 4 is negative 1. So if I added up every term in this sequence right here, I would get a negative 1. Once again, let me know if that doesn't make sense. All right, we have another special type of series that is called geometric. Geometric series is a series of the form, the sum from 1 to infinity of a times r to the power of n minus 1. So it's like a plus ar squared plus ar cubed, on and on. And what's really nice about this is what I can say is that if the absolute value of the r is less than 1, the series converges. In fact, the sum would be a divided by 1 minus r. If the absolute value of r is greater than or equal 1, the series is going to diverge. Okay, so let's use that fact. Example number 3. I'm going to determine if each of these converges, and if it does, find what the sum is. It's the sum from n equals 1 to infinity of negative 2/5 to the n minus 1. All right, so I can tell right away it looks like this does, right? Because I have something to a power of n minus 1, so I'm looking good, okay? So what I need is just to state what a and r are. Well, there's not a number in front of this, right? So a is just 1. And then r is what's being raised to the power. So r is going to be negative 2/5. So let's take the absolute value of r. That's going to be the absolute value of negative 2/5, which is just 2/5, which is less than 1, which is telling me this is going to converge. Not only that, but I know the sum is a over 1 minus r. A is just 1 over 1 minus, and then r is negative 2/5. That's like saying 1 plus 2/5, which is 7/5. 1 over that means I just flip it over, and the sum is going to be 5 over 7. Easy enough. If that doesn't make sense, though, let me know. Example B. Sum from n equals 1 to infinity, e to the 2n. So what's being raised to a power here is e. Again, there's nothing out front, so a is just 1. What's being raised to a power is e. Technically, actually, I would use e squared because this is e to the 2n is like saying e squared to the n. So then I would use e squared. But that doesn't really matter because the absolute value of that is greater than 1 because e is like 2.71 something something. So if I squared it, I know it's at least 4. You know what I mean? Which is greater than 1, so this diverges because it's greater than 1. And then example C is going to require a little bit of work. N equals 1 to infinity of negative 3 to the n plus 1 over 4 to the n minus 1. Now let's think about why this is going to require a little bit more work here, okay? So I want to know what r is, right? And r is just the thing being raised to a power, right? Well, I have a power here and a power here. Since they're not the same, there's nothing I can really do, right? So what I really want to do is make this to where these are the same thing, okay? So I want on top to have negative 3 to the n minus 1. So I wanted to have negative 3 to the n minus 1. But I had n plus 1. So how do I make this equal to negative 1, right? Well, what do I do to the negative 1 to make it plus 1? Well, I have to add 2. Again, because I want the minus 1. Using our exponent rules, since I'm adding the powers here, I can write it as negative 3 to the n minus 1 times negative 3 squared, because it's plus 2, so then I can make it a squared. Negative 3 squared is 9, which is a constant, which I can bring out front. And this becomes negative 3 to the n minus 1, 4 to the n minus 1. Now they are the same, so I can combine them like that. So now I can see that my a is 9, my r is negative 3/4, absolute value of r is the absolute value of negative 3/4, which is 3/4, which is less than 1, so I'm good. So this is going to be a, which is 9, over 1 minus r. 1 plus 3/4 is 7 over 4. Flip that around and you end up getting 36 over 7 for that sum. If that doesn't make sense, please reach out. I will be happy to help you to do out. The last special kind we are going to talk about in section 5.2 is the telescoping series. This is a series in which most of the terms cancel each other out whenever I do the partial sums, leaving only some of the first terms and some of the last terms. So an example is when I look like this. So bn minus bn plus 1. So for the first term, it would be a1 minus a2. Then my next term would be a2 minus a3. Then my next term, a3 minus a4, and on and on and on. So when I add all those up, I'm canceling out a bunch of stuff. Let me show you what I mean. So like if it was like what this example said, bn minus bn plus 1. So my first term would be b1 minus b2 plus, then my next term would be b2 minus b3 plus, then my next term would be b3 minus b4 plus b4 minus b5, on and on and on. We'll look at what's happening here. Negative b2 plus b2 cancels out. Negative b3 plus b3 cancels out. Negative b4 plus b4 cancels out. And that'll keep happening forever and ever and ever. This is what's called telescoping. They're canceling out. So how I'm going to see what's happening here, telescoping series, which is what we just said, converges if and only if the sequence bk plus 1 converges. Furthermore, if bk plus 1 converges to something, we'll just say b, then the sum is b1 minus that b. So I'm going to look at what happens to my last term, and that will help me out. So, example 4a, the sum from n equals 1 to infinity, e to the 1 over n minus e to the 1 over n plus 1. So what I'm going to do is I'm going to look at what happens on the last term. So the limit as n goes to infinity of e to the 1 over n plus 1. Well, what happens there as n gets really big, the bottom part here gets really big, which means the whole thing up here gets really small. So this becomes e to the 0, which is 1. So my last term is getting closer and closer to 1. So everything is going to cross out except for my first term. Plug in a 1 for the first term, and that's going to be e to the first, minus my last term, which I have already said is approaching 1. That's it. Another example, just to make sure that's clear. Sum from n equals 1 to infinity of cosine 1 over n minus cosine 1 over n plus 1. Let's look at what's happening on my last term. So that's the limit as n goes to infinity of cosine 1 over n plus 1. We've said we can switch these since cosine is continuous. Once again, as the bottom gets really big, the whole thing is really small. So this is cosine of 0, which is 1. So I take my first term, plug in a 1, you get cosine of 1, which you can't rewrite some other way. So cosine of 1 is fine. Minus my last term, which is approaching 1. That's it. If any part of that does not make sense, don't be afraid to let me know. I will be happy to help out.